What's up, everybody? Welcome to Earth Science. What we want to look at today are raised relief globes. These guys right here. These globes that have little bumps imprinted on them for the mountains. And in fact, if you're doing this in class, I'd like you to get up quick, come over here, check out this globe, see what it feels like. Feel the Himalayas, Rockies, Andes, whatever. What do they feel like in terms of what your guess would be for how big they should be? Do they feel about right? Do they feel like they are to scale the size that those mountains would actually be? Do these Himalayas right here? This is the tallest mountain range on Earth right now, where India meets Asia. Sorry, I'm trying to do this in the camera. This is the tallest mountain range on Earth right now. So do these bumps on this globe feel appropriate for that? Also, how round is this? Is this a perfect sphere? If so, how does it compare to the Earth? Is the Earth perfectly round? Is the Earth perfectly smooth? No, neither one. How round and how smooth are they? And what would make a good model for that Earth? All right, so we'll do it in two parts. Now, listen, this lab is maybe slightly chunky, slightly get lost in the weeds with some arithmetic. I'm going to help you through the whole thing. Okay, so really, this should be pretty much a free 30 out of 30 for almost everybody. The only question you're really going to have to it's going to be two, like this one right here. And the very end, I'd like you, since I did the whole lab, is to give me a couple sentences here that show that you're figuring out what we're talking about. Other than that, I'm gonna help you through all of this because it is a bit messy. So a raised relief globe or map has these features so you can see what's going on. How accurate are these? So what's your guess? Do you think those mountains are too big, too small, or just about right? So we're gonna do it because it's just a heck of a lot easier. We're going to do it. We're going to pretend that this is the globe that you're going to use. So it'd be like if you took this globe, cut it in half, took a slice out of it, and looked at it from the side. How accurate is it? With Mount Everest right here, if that Mount Everest is the height on the relief globe, and I'm thinking that it's about right. It feels like it's a bump that's about that big. Um, how accurate is that? How round does this look? I mean, if we just take a peek at it here, let me zoom out a little bit. It looks pretty darn circular. How round is this compared to how round the real actual Earth is? So part one is roundness, part two will be the smoothness. Earth's actual shape is called an oblate spheroid. That's Oblate spheroid. Oblate spheroid. It means it's a little bit squished at the poles. So it's spinning towards the east, right? So it's spinning this way. And that's going to like push out here at the equator. So it's really like if you took the globe and just like smushed it a little bit that way, it'd be a little stubbier from pole to pole and a little fatter around the equator, but not really by much. So in fact, we can just do this as a ratio. And again, if this math looks like Mr. F, I don't know what you're talking about, don't worry about it. Don't panic. We're just going to compare the diameter from pole to pole to the equator to the diameter across the equator. Easy peasy. If they were exactly the same, you'd be dividing a number divided by the same exact number. And if you've got a number on top and a number on bottom and they're the same, the answer is 1. So I'm going to write that over here. If it's a perfect sphere, the roundness ratio would be 1. So basically, however far away you are from 1 means the less round you are. 1's perfect. Further from that you get, the less round you are. So we're going to take these two, 12,714 for Earth's polar diameter, 12,756 for Earth's equatorial diameter, and we're going to divide them. And I'm going to get 0.997 for Earth. Pretty close to 1. That is a 9. Pretty close to 1, therefore pretty darn spherical. Even though we're taking the time to announce and to study that it's not perfectly spherical, 0.997 is pretty darn close. How about the relief globe? So here's what I'm going to do. I'm going to do it on paper, though, because it's easier. I've got it right here and a ruler, and we'll measure them. All right, so the polar diameter On this one, I'm getting 15 on the dot. So 15.0 centimeters. Equatorial diameter, 15.5. All right, so the roundness ratio of that again looks pretty darn spherical. 15 divided by 15.5. Excuse me. Oh, lost it. Was it 0.968? So is the Earth a perfect sphere? No. I mean, use data. Tell me. The polar diameter and the equatorial diameter are different. Therefore, it's not a perfect sphere. It's got to be off by a bit. Which of the two, the Earth or the relief globe, is closer to a perfect sphere? Which one's closer to one? One is perfect. Which one of those two numbers is closer to one? So I'm going to use some data, complete that. You can hit pause here if you want. I want decent sentences. Again, I think it's 3 sentences total that I'm going to have you do. 3 questions total I'm going to have you do. Give me some decent work there. Okay. Part 2 is smoothness. So what we're going to do here is a ratio, the way you would for a model. Let me grab a model, and I need my model Earth. All right, so a scale model. What is a scale model? This, when you see these around, scale model of a World War II tank, which I never finished building, but there it is, partially done. What's the point of these things, though? What they want is that everything is exactly to scale the same way that the real version would have been at the moment. If you had one of these tanks, this is a miniature version, but it's scaled down such that these little wheels, the chassis, or whatever it is, the turret, they're all shrunk down by the same amount so that the whole thing is done to scale, right? So if we were to do that, you could do that using this equation right here. We're going to do that with the Earth. How big are these features on the model? How big are these features in real life on the Earth? And then we'll just compare them and see where we are size-wise. Again, I'm not saying that this math is going to be like intuitive, and it might be like for a few minutes like, what is this guy talking about? Because we're going to run some numbers, do some quick cross-multiplying, things like that. If you get lost in the weeds, just stick with it. And again, we'll get to the point at the end, and we'll talk about what we're really trying to figure out here. Okay? So first, let's figure out how tall Mount Everest should be on a raised relief globe. So we'll take the data of the real life Mount Everest and figure out how tall it should be. All right. I'm going to change to a smaller pen here. So actual height of surface feature from Mount Everest, 8.8 kilometers. We'll start with that. Earth's actual diameter, which I'm just going to steal this one from up above, is 12,756 kilometers. Relief height, how tall would that be on the globe? Well, that's what I'm trying to figure out. So that's going to be X, and we'll divide that by the size of the relief globe, which was 15.5 centimeters. And this what this will answer for me. And again, if you're getting lost, what this will answer for me is how tall should Mount Everest be if it's a real life scale model on a globe that's 15 centimeters across. Okay? So we have to cross multiply. This is going to take a sec. Be patient. You'll get there. 12,756 X. And I did that. I see folks around here like to do the circling thing. So I'm doing that multiplied by that. So 12,756 X equals 8.8 times 15.5, 136.4. And then we will divide by 12,756 to cancel that out on both sides. And the height of Mount Everest, then, what it should be if this were a scale model, is 136.4. Sticky keyboard, that's not good. divided by 12,756 would be 0.011. We'll go with that. 0.011 centimeters tall. That's how tall it should be. That's a tenth of a millimeter. On a ruler, those little tiny lines are millimeters, and we're saying a tenth of those. Tiny, 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 tiny. So, how far off is this globe then? If we measure Mount Everest on that globe, I've got it at 0.3 centimeters. We'll just chuck that in here, 0.3 centimeters. So percent error is something that used to be in the earth science course. They've taken it out. Now it's only in chemistry. But it's basically how far off are you as a percentage. So fortunately, we don't have to deal with these things anymore. 0.3 centimeters minus that, which is what it should be, divided by what it should be, times 100. And again, this is one of those things where I'm going to say, hey, listen, just stick with me. If this is like, dude, what are you talking about? Don't worry, don't panic. All I'm doing is I'm showing percentage wise how far off is this. Is this too big, too small, and how far off is it? Well, it's clearly too big because it's that big and it should be that big. So percentage wise, how far off are we? 0.3 minus 0.011 divided by 0.011 times 100. 2,627. That's your answer right here. So at the beginning, if you said those mountains are too small, or maybe those mountains are just right, they are in fact way too large. They're 2,627% too large. Way, 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 way too big. Okay. So that's the premise here. What does that mean about the shape of our Earth? It's actually going to be very, 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 if these are way too big, bells are in videos. You guys hate that. If those are way too big, what is the actual surface of the Earth like? It's actually going to show us that it should be very, very, very smooth on this scale. Because the planet's so big, even a big old thing like Mount Everest doesn't end up actually looking that large. So this is like, we're going to do the same thing again, hopefully a little faster. And what it's going to do is say, all right, well, if I took this globe then with its Mount Everest that's 0.3 centimeters large, and I blew the globe up to the size of the Earth, how tall would that Mount Everest end up being? So this time, I don't know what the real height is, x, on that globe that is 12,756 kilometers. If on the globe it's 0.3, on that 15.5 centimeter globe. Oops, skip the 5. 15.5 centimeters. Cross multiply again, just like we did before. So 15.5x equals 12,756 times 0.3. $3826.8 over 15.5 over 15.5. 246, let's call it 0.9 kilometers. Okay, what are we doing here? If we got lost in the weeds, what this is telling us is that if a relief globe has one that's 0.3 centimeters tall and I blew that relief globe up to the size of the Earth, it would be 246.9 kilometers tall. That's how tall that mountain would be. Now, Mount Everest is huge. People get killed climbing it all the time. And in real life, it's 8.8 kilometers high. What if it was 246.9 kilometers high? That would be completely ridiculous. It wouldn't even work with the physics, with the laws of physics we have and gravity and how all of that goes. So I'm just copying that number again. And if you look at your ESRT, page 14, I'll pause and find it and skip the next bell. We haven't really dealt with this one a lot yet. You looked at a quick and density of liquids, just say, hey, here's your 4 layers of the atmosphere. But troposphere, everything you've done is in the troposphere. Then there's the stratosphere containing the ozone, mesosphere, thermosphere. We don't really end up talking about those much. But look, those, even the top of our reference table only goes to 160. Guess what's up above that? So basically, if you climbed that mountain, if it were 246.9 kilometers tall, what layer of the atmosphere wouldn't even be in the atmosphere? You'd be in outer space. That's almost as high as the International Space Station. So you could climb a mountain and knock on the space station door. Does that seem to make sense? No, that's not something that's going to happen. All of this, making a short story long, is the idea that Mount Everest is way too big. In real life, Mount Everest is only 8.8, which puts it in that bottom layer of the atmosphere, the troposphere. All right. So let's get to it. What object really wouldn't make a good scale model of the Earth? If this is not good, because the Earth is actually rounder than this and the Earth is actually smoother than this, what is good? When I have people guess, they'll oftentimes guess a basketball. But the little tiny bumps on these basketballs, again, would be the same deal. Those would be mountains that make it into space. These black lines where the seams are would be ridiculously deep caverns. So deep and so tall that like geology doesn't even let it work that way. With the weathering and erosion, things fill in and wear down. Or if mountains get tall, they sink back into the smushy part of the earth anyway. So this would not work at all. So this is the answer. And this is a crazy idea right here. Stop and listen to this one sentence. The real Earth is even rounder and even smoother than this pool ball. And you guys know how round and smooth these are, and I'll have this too if you want to check it out. Feel it. Roll it. You'll see that it's incredibly round and incredibly smooth, but the real Earth is even rounder and even smoother than this is. And you might say, well, I've seen the Grand Canyon on TV. I've seen Mount Everest on TV. Maybe I've been to some of these places. They're huge features. Yeah. But if you can find a little scratch on this pool ball, like there is one here, if you were to take this and blow this up to the size of the Earth, that would make the Grand Canyon look like nothing. The Earth is so large that these features would be like that on that scale, just don't really show up so much on these small scale things. So if you were a giant alien so big that your hand was this big and the Earth was this big and you felt it, you could probably tell where oceans are and stuff like that. But really, it would feel as smooth as this is, even with all of our mountains and all of that stuff. It would feel that round, even though it's an oblate spheroid, even though it's a little bit smushed. This, I'll say it one more time, is less round and less smooth than the actual Earth, mathematically. So, but it's still a decent scale model, a pool ball, because it's very round and smooth. Not as round and smooth as the real Earth. The real Earth is incredibly round and incredibly smooth. Okay. I think I'm just going to skip this one this year because the cross multiplication thing, I'm not worried about actually doing it. Excuse me. But basically, what it says is if you put a millimeter, a tenth of a centimeter scratch into a globe and then blew it up, it ends up being way, 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 way bigger than the Grand Canyon. So we'll legally skip these two because I think we've gotten the points. Gone, gone. This is going to leave you only with this to do. And I want a decent answer. I've done this whole lab for you, and I know it was a little bit heady right there, right? But what's the point of the lab? You tell me. Um, and it says this is our first shot at practicing using lab info. And I think we've maybe done a little bit of it. I'm going in a slightly different order, but can you write a couple sentences that tells me the point of the lab? keeping in mind this is not as round and smooth as the planet is, but use numbers to support that claim. If I don't see numbers, this is coming right back to you incomplete instantly before I even look at everything else. I got to see some numbers here for this answer to like meet the qualification. Tell me how round and smooth the planet is. Compare it to a good scale model of a planet or a bad scale model of a planet, but use numbers to tell me that information. And you can steal numbers from any of this stuff. Okay? That's really the one thing I'll look at. I'm going to look there, see if there's numbers. If there's no numbers, it's coming right back to you incomplete till you fix it. Then I'll come back up here and check these two questions. Make sure you give me a couple of thoughts there. And then it should just be a 30 out of 30. And I know that it was a little bit of a long video, but you fought through. You did a good job. 30 free points on the lab. Thanks, everybody. Take care.